Good morning. Hope we can start now.
Good morning, sir.
Good morning, sir.
Good morning. Yes. Right. I think in the previous meeting, we came up to the point that for a continuous variable, when it comes to calculating the probability, the basis is area under the curve. Area under. Remember what we said. Then we said that area is obtained by integrating function between respective intervals 140 to 160, 170 to 189 points. Right. So ultimately, what we said that it's a matter of calculating two area values. Matter of calculating two area values. One is for the interested interval, say A1, and then the total area. A. And thereby we can have probability x between A and B to be equal to capital A1 divided by capital A. And then what we said is the challenge is function of the curves. And now you see, we need to integrate the function. Now the question is, what is function? I told you that this is the most common distribution we find for continuous variables. Not for all, but for most. Since this is the most common, I think I told you yesterday, this distribution is known as normal distribution. As you can expect, since this is the most common, obviously everybody finds it to be interesting. At least a lot of people find it to be interesting, so that they have studied that long time ago. They found the properties of this normal distribution. Since it is so common, people found the function of this curve. So this is now, you can call it to be normal curve. Normal curve. Curve representing the normal distribution. Normal curve. And then function of the curve to be fx is equal 1 over square root of 2 pi sigma square, and then e to the power minus half x minus mu divided by sigma whole thing to the power 2. People found this to be the function of this curve, or the function of the normal distribution. Now recall, what is this curve? What is this curve? Is for the curve of the distribution for the density histogram. Density histogram. Okay. Because of that, we call this to be the density function of the normal distribution. Density function of the normal distribution. Right. Properties of the normal distribution. normal distribution. Well, you can see that it's symmetric, and then symmetric around mean, and then mean is equal to median is equal to mode. Theoretically, it goes from minus infinity to plus infinity. Minus infinity plus theoretically. Okay. Because of that, when drawing the curve, make sure that the curve does not touch the x-axis. Does not touch. Because that infinity. Infinity in the sense that you don't know what the value is. So theoretically, it goes from minus infinity to plus infinity. We can have values, the normal distribution, we can have values from minus infinity to plus infinity. There is an inflection point. What do you mean by inflection point? Now this is mean, and then we can think of a line from this mean axis to the curve, to the point. I said that on this curve, you find a point which is called an inflection point. What do you mean by inflection point? Inflection point is a point of kind of this form. Okay. So curve is onto both sides of this point. Curve is increasing. See, increasing. Before the point as well as after the point is decreasing. But at this point, slope is equal 0. I think you will come across this very soon in the maths course if you haven't come across already so far. Okay. And interestingly, from the curve, from this mean axis up to that inflection point, the distance is sigma. What is sigma? Sigma is the standard deviation. And inflection good. We have already done that in the maths course. And if you think of one standard deviation onto both sides of mu, so likewise on this side also you have an inflection point. This is sigma. We are talking about like 68% of the area. Area between mu plus or minus sigma is 68%. And then if you think of mu plus or minus 2 sigma is about 95%. It's about 95%. So you can see how characteristic normal distribution is. Just 2 standard deviation, you are talking about almost all values. Theoretically, it can go from minus infinity to plus infinity. So that you can see outside 2 standard deviation, you find only very few values. That shows how characteristic it is. Values are concentrated around the mean. Most of the values you find just around the mean. So these are kind of common properties of the normal distribution. Okay. So, as an example, now you're talking about, remember, calculating area. Then the challenge was what? Function. Now we know the function. So that if you're interested in calculating the area, what you want is a, b. Now you integrate that function between a and b. And thereby we can find this area. And similarly, if you integrate between minus infinity and plus infinity, you get the total area. And thus you are in a position to calculate probability. Yeah. Right. I'm not very sure whether you have come that far in the math course. Possible, since this is kind of halfway through. Well, integrating a function. In fact, any function can be differentiated, but all functions cannot be integrated. All functions cannot be integrated. This function actually can be integrated, but the thing is that even if you're familiar with the technique integration, integrating this kind of a function is not that straightforward. It's fairly complex. Integrating this kind of function is not that easy. Okay. I told you that people started studying this curve about 2 centuries ago, or even more than that. But in 18th century, people started studying this. The person who discovered this curve is called Gauss. Person is a German. If you have been to Germany, those who have been to Germany, or those who have come across German currency notes, still in one of the notes, they still print that person's photograph as well as this normal curve. Is to respect that person, because it is so important as well as so close to the life normal distribution. Because as I said that for most of the continuous variable, you find distributed distribution. Can you believe that? Nature is such that this is how we have the nature. So you don't find kind of the values at every place to be more or less same. And see, most of the values you find around the mean. Away from that, you find very few. Yeah. That's how the nature is built. As I said, most of the variables, this is how you find it. Okay, right. So that we call this to be Gaussian curve as well. Gaussian curve. Gaussian distribution. It's please make sure that your mic is muted. Okay. Okay. Right. So I said integrating this kind of function is not that easy. And then we are talking about 3 centuries ago. Said these days, when it comes to do the integration, well, we can use what? Computers. You don't have to do the work. Even if it's difficult, you don't even feel it like it's difficult. Why? Because we don't do the work. We use computers. So computers do the job for us. Those days, of course, computers was kind of, well, 3 centuries ago, we didn't have something called computers. So then people have very difficulty in performing this integration. Well, to facilitate the requirement, those who could do that, mathematically strong, calculated these values and presented by means of tables. Presented by means of tables. So that others could refer to these tables and then find the probability. Because of that, or thanks to them, people could find the probability associated with the normal distribution without actually performing the integration. Mind you, this is a continuous situation, continuous case. So that when it comes to the integration, you can think of infinite number of points as well as intervals. Calculating areas for infinite number of intervals is not possible. Doesn't make sense. Okay, so that people tabulated these values up to an increment of maybe something like 0.05 on the x-axis, whatever the x scale. Increment of 0.05, so that corresponding to those values, well, we could find the probability from those tables. Between those increment points, well, obviously we had to rely on an approximate value, a value between those two values. Okay, right. Now looking at the function, it's yet another function like y is equal mx plus c. Y is equal mx plus c. Now, when you say y is equal mx plus c, or else y is equal fx is equal mx plus c. So y is a function of x. Okay. So in this function, x and y are whole variables, including y. Y is on the left-hand side, of course. X and y are variables. What are m and c? M and C are given the curve, M and C are constants. Given the curve, M and C are constants. But they are not universally constants. Then curve to curve, those values vary. Because of that, M and C are the parameters. So mx plus c function of the form mx plus c is a 2-parameter function. The parameters are m and c. Similarly, normal distribution. Okay. What are the parameters? Now, see, 2 is a constant, Pi is also constant. Now sigma varies from distribution to distribution. So sigma is a parameter. And then E, what is E? E is the base of the natural logarithm. E is a constant. It's the base of the natural logarithm. E. You can get that from the calculator. 2.71828. Likewise, that's how you have. Okay, it's an irrational number. Remember, numbers that you all discussed is an irrational number. I suppose I asked everybody to have a calculator ready. Did I on the first day? Well, I hope so. Because Kamal, Amal said that Kamal joined only yesterday. All right. Tuman sir,
Yes, sir.
were you around from the first day?
Uh,
When did
uh,
was it in second day from the first day itself?
I was late on first day.
You were late on the first day, although you were around on the first day. I'm not very sure since nobody responded, anybody else responded. Gamage, Kiki Gamage,
Yes, sir.
were you around on the first day?
No, sir.
No, okay. Right. I'm not going to ask anybody else. Right. In case if I didn't tell, I suppose I said that calculators are allowed during the examination. Okay. So this thing is that be familiar with the calculator. These days, the way you operate the calculator varies from calculator to calculator. So best thing is that get familiar with the calculator. Otherwise, you will have a tough time using the calculator. If you think you just bring it to the calculator examination and then start using it, you could be in big trouble. Okay. And then you are not allowed to share the material. You cannot borrow it from another person and use it. Okay. It's not allowed. So if you bring a calculator, you can use it. And if you don't bring a calculator, it's your problem. Well, others are not responsible for that. Don't expect to share it from another person. Is that clear? Just right. Right. He said you can easily get this value from the calculator. And then E is the constant. And then the importance of this constant is that this is the base of the natural logarithm. Natural logarithm. Normal logarithm, what is the base? Normal logarithm, base is 10. Base is 10. But, well, natural logarithm is much more useful. A lot of natural phenomena can be described using logarithmic functions based on this specific base. Okay. Base 10 is very convenient. Yeah, that's it. Yeah. We are kind of easy to work with, but when it comes to usefulness, you find it to be natural logarithm to be more useful. Right. So E is a constant. And then, well, 1 and 2 obviously are constants, and then x is a variable. X is a variable, and then mu. Mu is a mean. So mean is another parameter, and then sigma again. So that you can see normal distribution. If you want, you can have that also as a property. 2 parameter distribution. It's a 2 parameter distribution. And then perhaps something specific is that, let's say, 9. We often use a word to describe the shape of the distribution. We call it to be bell shape. I say it's symmetric around mean, and then mean, median, mode overlapping. Likewise, we said that, and the shape of the distribution is bell shape. Now, in order to understand more about the meaning of these parameters, so normal distribution is a bell shape. So that see, this is one distribution. Okay, probably this is another distribution. So mean is here, let's say mu1. This is mu2. Naturally, you can see mu2 is larger than mu1, isn't it? Because this is 1, 2 from left to right. Left to right, the values are increasing, isn't it? So mu, this distribution is located around mu1, and this distribution is located around mu2. And the spread of this one is smaller than spread of this one. Exactly. So this is what is meant by the parameters. So that 2 parameters are associated with what? First one, mu is about what? Mu is the location parameter. Mu is the location parameter. And then sigma is describe the spread. Is the dispersion parameter, otherwise it's about the spread location parameter. It is mu represent what? The location where the distribution is, and then sigma represent what? The spread of the distribution. Okay. So that the function we describe is like y is equal mx plus c. Depending on m and c, we are talking about different curves. Depending on m and c, we are talking about different curves. So likewise, depending on mu and sigma, we are talking about different curves. So y is equal mx plus c describe what? Family of linear functions. Family of linear functions, and then depending on m and c, we are talking about different functions. If m is equal to 2, c is equal to 5, then we are talking about a specific function. Isn't it? Right. So that mx plus c represent family of linear functions. And similarly, the function we described there earlier for the normal curve is the function of the family of normal distribution. So if mu is equal to specific value and sigma is equal to a specific value, then we are talking about a specific normal distribution. Like m is equal to c is equal to 5. Okay. So earlier we said fx is equal 1 over 2 pi sigma square e to the power minus half x minus mu divided by sigma whole into the power 2. Okay. So that example, mu is equal 0 and sigma is equal 1. Then what we have? Fx is equal 1 over 2 pi sigma. Sigma is 1. 1 square is 1. So square root of 2 pi e to the power minus half uh, 1, well, x minus half and then x minus 0. X minus 0 is x. And then x divided by 1 is x. And then whole thing to the power 2. Okay. Likewise, now mu is exactly 0. That's how I took it. And sigma to be exactly 1. So it was simple situation. Okay. But as you can see, by substituting mu and sigma in terms of exact values, then we will have a specific normal distribution. In fact, this particular case is a special case. Although I took that as an example, it's a special case. Mu is equal 0 and sigma is equal 1. It's a special case and it is called standard normal distribution. So that this density function is the density function for the standard normal distribution. So standard normal density function of the standard normal distribution is slightly less complicated, isn't it, compared to the general case. So bit simplified because mu is equal 0 and sigma is equal 1. Standard normal distribution. And I see we have fill up to 9 points and then as one more 10th property, we can have it like, remember we were talking about this is the function of the curve of what graph? Density histogram, remember? Curve of the density histogram. Density. Density. Relative frequency is presented by means of area. Relative frequency. Relative frequency. Once you add the relative frequency, what value do you get? Once you add the relative frequency, first column is up to 0.1, second column, let's say 0.2, third column again 0.15. Likewise, if you add those values, what value do you get? 1. Sum of the relative frequency should be equal to what? 1. So that here too then, since we are talking about density histogram, sum has to be equal to what? 1. Sum has to be equal to 1. Okay. Thing is, if large number of values are to be added, you can see we are talking about how many values? Infinite number of values. Isn't it? Infinite number of values. So adding infinite number of values is not possible. So easy approach is what I think we have again studied in the maths course. Integration is alternative approach of what? Summation. Integration is actually summation. Okay. More efficient method of adding values, especially when large number of values are there to be added. So that sum has to be equal to 1. Integration. Instead of adding 1 by 1 infinite number of values, you calculate the area. You calculate the area. So area then has to be equal to, since sum of the relative frequency is equal to 1, the area under the curve should also be equal to total area under the curve is equal to 1. Well, when you have total area under the curve to be equal to 1, what is the advantage? Now remember earlier what we said is that ultimately calculating probability is a matter of calculating two area values. What is that? Area for the interested interval, area for the interested interval, and then the total area. Isn't it? If the total area is equal to 1, then we don't need to calculate the total area. Well, I mean, we know it's 1. So that this area is always a value between 0 and 1. So that this area can directly be interpreted as probability, because this area value divided by 1 is this area value. So the advantage of area under the normal curve is that the area for the interested interval can directly be interpreted as probability of having a value between those 2 points. Okay, because total area is equal to 1. So now we are talking about, it's a special case. Mu is equal to how much? 0. Mu is equal to 0, and then sigma. Mu is equal to 0 and sigma is equal to 1. Okay. Theoretically it goes from minus infinity to plus infinity. Okay. And what I said is, people have studied this normal distribution in detail. Area values have been produced by means of tables. In fact, that area has been computed for this specific distribution. That's why I said that this specific distribution is a special case. This is what is standard normal distribution. People have calculated the area values of this standard normal curve. In fact, standard normal curve is denoted by, or the standard normal variable is denoted by Z. Okay. So now standard normal variable. Standard normal variable is denoted by, now we see as height. Height is a variable. Likewise, now Z is also variable. Height is having mean, and then standard deviation. Likewise, now we have denoted this special normal distribution as standard normal distribution, so that normal distribution is normal distribution of a variable. So that Z also denotes what? Variable. question could be that why do you want to label that as Z? Then label that as Z or Z or Z. Reason is that usually variables are denoted by what letter? X, Y, isn't it? Whenever we want to denote a variable, we use the letter X, that is the starting point, and then Y, likewise. Those are the two letters commonly being used. After X and Y, what is the letter in the alphabet? Is Z. Because of that, people started using Z to denote the standard normal distribution. Okay. Standard normal distribution is a specific variable. Normal distribution is not a variable. Normal distribution is a distribution. But Z as a variable, but Z is a special case. Z is a special case. Z is a specific distribution. So variable that has that specific distribution is called standard normal variate, or otherwise Z. Okay, so that is the reason behind labeling the standard normal variate as Z. So now, when you say distribution, we can recall distribution of X. Likewise, now what is this? Distribution of, this is distribution of Z. Distribution of Z. Okay. So as an example, now see, right in the middle, the value is equal to 0. Value is equal to 0. And then somewhere here, suppose it is A. So we are interested in what? Probability Z less than, say, less than or equal to A is what? This area. Theoretically, what we have to do is to integrate this function. But now, as I said, that these values are available by means of table. So by referring to the table, we can find the appropriate probability. So that this table is of the form, you have the Z value and the P value. Z value and the P value. And then you find the Z values for an increment of something like 0.05. Said that something like for an increment of 0.05. But you find not just one format for the table, you find sometimes very detailed tables. In such detailed tables, you find probability for Z increment of something like 0.0001, likewise. So, as an example, let's say 2. After that, 2.0, 2.01, or there's 2.05, 2.10, likewise. And then on to the right, you find this area. Let's say P. So that's what you do. Okay. So Z is equal A, since that suppose so whatever, so I took this as general value A. So if you are interested in A, from Z column, you should find the A value, and then the value on to the right, the corresponding value under P is under P. So you have these values. So if you want corresponding to A, then find A from Z column and then read it on to the right. So this is the area, or the P. So likewise, by reading the table, you can find the relevant P value. Okay. Let me share one such table. I'm going to pass it through the chat. Right. Hope everybody received that table. Check and see. Right. Probably before getting into this, let me. Oh, God. Let me share another table. Right. Did everybody receive those tables?
Yes,
Yes.
sir.
Okay, good. First, look at the second table I shared. Okay. So this is exactly what I drew on the screen. So you see A, we are interested in this probability. So all what we have to do is to find A from the Z column. Find A from the Z column and read it on to the right. Thereby you get the p-value. Now, as an example, if I say, what is the probability Z less than or equal to 0? Now, for this, do we need a table? No, we don't need a table. Why? By argument, we can get the value. Everybody knows this value. Well, you can see 0. Where do you find 0? Right in the middle. Right in the middle. Onto the left of 0, you find half of the values. Onto the right, you find the balance half. Meaning the distribution is symmetric around 0. And we know the total area under the curve is 1. So then we should find half the area less than or equal to 0, isn't it? So this is 0.5. For this, we don't need any integration or otherwise table. But now, obviously, if it is any other value, obviously, by argument you cannot get, then we need to refer this table, or otherwise do it by integration. Right. So the idea is that using the table, we can get the value. Now, let's check whether the table is correct or not. See, did everybody hear that? Let us check. Meaning, see, as humans, well, we can check that. Of course, it is generated by a computer, but still we can check and see. We are not below a computer, we are above a computer. Right. So let's see. So what I said is, now look at the table, this table, second one. How many columns are there? Theoretically, we find 4. Altogether, you find 10 columns in it. But the thing is that in reality, how many columns are there? 2 columns are there. What are the 2 columns? Z and P, isn't it? Z and P. That's all, because here also what you have is Z and P. So only 2 columns are there, but it has been organized into 10 columns. Right. Now you can see that in the Z column, very first value is minus 2.6 and the next value is minus 2.58. Now remember I told you that you find the probabilities are given correspond to Z values for Z value increment of something like 0.05, 0.01 likewise. So here for an increment of 0.02, for an increment of 0.02. Okay. So in between, as an example, minus 2.59. What is the probability? So probability that we read is that starting from minus infinity up to that point, up to this Z value, whatever this Z value. Okay. This area. So it's always a left tail area. So if we say this is tail, left side area. Yeah. So let's check whether the table is correct. So first we need to find Z value 0. Where do you find Z value 0? Z 0 you find here. Now read it onto the right. What is the value? 0.5. 0.5. So now you can see that. But table is correct, isn't it? So if one value is correct, you can expect that other values also to be correct, so that we can use this table to get the probability. Okay. Now, as an example, some other Z value. Suppose we are interested in probability Z less than or equal to minus 1.2. Well, minus 1.2, say somewhere here, minus 1.2. So that this time by argument we cannot get that by looking at the table. Looking at the table, minus 1.2, where do you have minus 1.2 is here. This value, minus 1.2. How much is probability? 0.1151. Is that clear? 0.1151. Right. Probability is at greater than 0.2. Greater than 0.2. Now what I'm interested in is, we have got 0 in the middle. 0.2 is somewhere there. Well, I'm interested in this. But the table gives left tail probability. Table always gives left side probability. So if you want to get the right side probability, how can we get that? We know the total area under the curve is 1. So that from 1, if you subtract the left tail, then you can get the right tail. Probability Z greater than 0.2 is equal to 1 minus probability Z less than or equal to 0.2. This you can obtain from the table. Sorry. 0.2. 0.2 is somewhere here, isn't it? This is 0.2. And then left tail probability is 5793. Is that clear? So that by substituting five, 7, 9, 3, which is equal to 7, 0, 2, 4, 0.4207. So likewise, any probability can be read. You might be interested in probability for an interval somewhere in the middle, say like minus 1.4 to minus 0.2. You see, how do you get this probability? Table gives only the left tail probability, isn't it? Only the left tail probability. So what we can do is, first we can get the probability from this point up to there, or starting from minus infinity up to this point, A. And then again you can get the probability up to all together up to this point, let's say B, that is minus 0.2. Okay. So if you subtract first probability from the second probability, we get the probability for the required interval. Probability Z greater than A and less than or equal to B can be obtained as probability Z less than or equal to B minus probability Z less than or equal to A. This we can obtain from the table. Now, probability Z greater than, what did I say, point? Okay. Minus 1.4 less than or equal to minus 0.2. Minus 0.2 is equal to probability Z less than or equal to minus 0.2 minus probability Z less than or equal to minus 1.4. This you can obtain from the table, and this also you can obtain from the table directly. So by substituting, you can find the relevant probability. Okay. See, so this is how we calculate the probability for continuous variables. Ultimately, what did we do? We use this table. So we call this table to be standard normal table. Well, standard normal distribution, what kind of distribution is standard normal distribution? Well, any normal distribution is symmetric. Any normal distribution is symmetric. Imagine the case, this is 0. This is minus 0.2. Probability is at less than or equal to minus 0.2. And then, let's say this is plus 0.2. Probability is at greater than 0.2. What can you say about those two values? Since the distribution is symmetric and the distribution is symmetric around 0, two reasons. One is symmetric, the other one is that it's symmetric exactly around 0. Because of that, probability is at less than or equal to minus 0.2 is equal to probability is at greater than 0.2. isn't it? It's exactly the same. Since the distribution is symmetric, number one. Number two, it's symmetric around 0. So that, do we need actually probability values are given to plus values as well as minus values? See, when you have Z values given for one side, sorry, probability values given for Z values of this side, when these areas are given, these areas, or there's one Z value plus value, Z plus values, probability values are given, then we can work out the probability for the other side. So giving probability values for us, giving the probability values for Z values corresponding to both minus values and plus values is kind of redundant, isn't it? Because once you have the probability associated with plus Z values, you can always work out probability associated with minus Z values. You don't need actually probability values given for Z values corresponding to both plus values as well as minus values. So that sometimes the table is produced only for the plus Z values, or otherwise minus Z values. Somehow only one set of Z values, either plus or else minus. The first table I shared, if you look at the first table I shared, is in fact table in that form. So it says standard normal probability, P in left tail is altogether given, but as you can see as Z values, so these values are Z values, and then this is for the second decimal place. Okay, so only plus values are there. So the table entries, these values are these values are the probability values corresponding to these Z values. But Z values are given only for the right hand side, or the right half. Okay. Now, from this table also, Z corresponding to 0.00, 0.00 is this probability sum 0.5. Without table also, we know that value has to be 0.5. And probability Z less than or equal to 1.2. 1.20. How do you get that from this table? 1.2 up to first decimal point, you can find it from the first column, this column. And then 1.20 is from this column, 0.00. So how much is that? 0.88493. Is that clear? So that now zero 0.88493. P is at less than or equal to 1.31. 1.31. One point three from first column, and then 0.01 you can find from this column. So that we have the p value to be 0.90490. Exactly 90. Like that. So from this table, you can see you can find the probability values for Z increment of 0.01. Previous table for Z increment of 0.02 only we could find, but this is more detailed, isn't it? Why? Because well, I removed the minus values, thereby I save space, and I accommodated that space for Z value increment of 0.01. Okay. Imagine Z minus 0.331. How do you find this value? How do you find this value now from this table? Minus 0.31. Do you find minus 0.31? No, we don't find minus 0.31. We don't find minus 0.31. Right. And we know, using the properties of the normal distribution, so what we have? Question of interest is this minus 0.31. But something we discussed earlier is that if you identify plus 0.31, this area is equal to this area. What we are interested in is this area. Let's say P. But we know if you identify plus 0.31, this is also equal to B. And we know this one is probability. Go on. This P, probability is at greater than 0.31 is equal to 1 minus probability is at less than or equal to 0.31. Isn't it? It is equal to 1 minus probability is at less than or equal to 0.31. Now, less than or equal to 0.31, that we can get from this table. 0.31. 62172. Thereby, probability is at greater than 0.31. 0.31 is 1 minus probability is at less than 0.31. So 1 minus 0.627172 is 8, 2, 8, 7, 3. So that we can say probability is at less than or equal to minus 0.31 is equal to 1 minus probability is at, now it is equal to, probability is at greater than 0.31. And it is equal to 1 minus probability is at less than or equal to 0.31. Now we have found that value to be 1 minus 0.62172, which is equal to 0.37828. Exactly. So now you can see this table can be presented in various different ways, or at least in several ways. Whatever the table, you should be able to refer to the table and then get the probability.
Excuse me, sir.
Yes.
Sir, can you explain again the last example?
Last tips. Okay. Let us take another one so that we get maybe more exposure. So let's have now another one as a second one. Probability is at less than or equal to minus 0.53. Suppose this is what we are interested in. Graphically, it is 0. Then minus 0.53 you will find onto the left of 0, isn't it? This is what we are interested in. So when we want to get the probability, what we do, we use the table. Isn't it? Let's look at the table. Do we find minus 0.53? No, you find only plus values. Isn't it? You find only plus values. Right. Now the question is, how do you get then this probability? We know from the properties of the normal distribution, this probability is equal to probability that we get onto the right of 0.53. Agreed? Because the distribution is symmetric and the distribution is symmetric around 0. Exactly around 0. So what we want is now this probability. It is equal to the required probability. Now, this probability, how much is this probability? We know this probability is a right tail probability. But the table always gives the left tail probability. Table always gives the left tail probability. So that probability is at less than 0.53 is equal to 1 minus, sorry. What we want is at greater than 0.53, isn't it? This is greater than 0.53. Is equal to 1 minus probability is at less than or equal to 0.53. Now, this probability we can directly read from the table that I share. Now, 1 minus. Probability is less than 0.53? Less than 0.53. 0.5 here. 3. 0.03 is here. 0.5 and 0.03. The value is this. Isn't it? 0.70194. Z greater than 0.53 is 1 minus. Probability is less than equal to 0.53. Probability is less than equal to 0.53 is 0.70194. So that this value is 60892. 0.29806. Therefore, probability is at less than or equal to minus 0.53 is equal to 0.29806. Is that clear?
Yes, sir. Thank you, sir.
So that's how you find the probability. And it's possible maybe table gives, I said that for instance, in this area, all together up to this point, all together the left-hand probability. But sometimes it is given from only for the right-hand side, but up to 0. Up to 0. Possible only this value is given. Sometimes it is possible. Okay. This is the Z value that we read. Only this is given. See, likewise, it can be given in very different ways. And this part is how much? Altogether, this part is 0.5. Together, that part is 0.5. So that altogether less than is at this value, which is A plus 0.5. You always add 0.5. Likewise, the table can be given different ways. Okay, right. So it's about finding probability using the table. Thing is, these days we are using computers. This course, we don't have any practical session, so that within this course, you cannot get exposed to the use of computers. For the computers, in fact, computer does not remember this Z table in the memory of the computer. Computer, it is much easier to do the calculation rather than keeping it in the memory. Okay. Some people, also, find it to be like, it's difficult. Maybe more than remembering it, it's just get the calculation done and thereby you find the value. Okay, for the computer, it's much easier. Computer is doing, in fact, the actual integration. The advantage of actual integration is that now see, even from this table, suppose I ask the question, probability is at less than or equal to 1.316. Can we find this from this table? No. Because it is given only up to 2 decimal points. It is given for Z increment of 0.01. After 1.31, what we have is 1.32. We don't have 1.316. So that, see, you can have only an approximation. Is that clear? Sometimes you find tables, it is given for an increment of 0.001. From such a table, you can get this. But then, how about 1.3163? That cannot be found. But the computer goes by the exact value. What the computer does is, computer is doing integration. For the computer, doing the integration up to 2, or otherwise 1.3163 doesn't make any difference. Computer is exactly, effort is exactly the same. Just two values. First one is 2, second one is 1.3163. That's it. First one is like 2.0000. Okay, so you can get the exact values with the use of computers. But as you can see, that good old days didn't have computers. That's why these tables were introduced. And another thing is that we still use, because inside a classroom, we can easily go by these tables. You don't need that exact value. That exact value is not necessary, so that we can go by the approximate value we can get from the table. Right. So that is how we deal with probability. Well, this Z table, what is the purpose of the Z table? Is to read the probability corresponding to different Z values. Different Z values. But when the table is available, now the table is with you. You can use the table as the way you want. What we did was, corresponding to Z value, we read the P value. How about other way around? Given the P value, finding Z value. That is also possible, isn't it? Because we are talking about two columns. Z and P. Earlier what we said is from Z to P. But well, if you want, you can go by other way around, say P to Z. That is also possible. Mathematically, it is like, let's say, probability Z less than or equal to A is 0.3. How much is A? Then find 0.3 from Z column. Let's say this is 0.3. And then read it onto the left. This is A. That's it. Okay. Similarly, we can have case like probability Z greater than A and less than or equal to B is 0.8. How much is A and how much is B? How about something like this? Say A, B, 0.8. But thing is, this question is possible. Let's say you start A from somewhere there and then B up to here, and thereby also you get 0.8, isn't it? Now there are so many possibilities for A and B such that we end up with probability 0.8. So it's like no unique solutions. different people can end up with different values. So one can say minus infinity up to some value. C is 0.8. So many possibilities. So in this kind of circumstances, in order to obtain unique solutions, we consider this 0.8 around the center. So that half of 0.8, 0.4 onto right hand side, and the balance 4 onto the left hand side. Okay. So that now probability, if this is the case, so now A is here and B is there. So that now if I ask you, what is the probability? Sorry, is it less than or equal to A? Is how much? Onto the left of 0.4. Onto the left of 0 altogether after this point is 0.5. So then how much is this area? Is 0.1. Then, so now we know probability is less than or equal to A is 0.1. Now from the table you can find A. Okay. I think I need to get back to the table. Sorry, get back to the screen. Right. So we went through probability associated with Z variables. Discuss. Okay. So it's a matter of using the table. So easy, very straightforward. Probability values are listed. Just read it from the table. Probability associated with Z. So if the distribution is Z, then using this table you can find probability. But the thing is, all variables do not have exactly the standard normal distribution. Normal distribution is there, but not the standard normal distribution. Say, it could be interesting. Height less than or equal to 145. Right. Okay. 145. This is what we're interested in. Height. This height is distributed as standard normal distribution. Standard normal distribution? No. If it is standard normal distribution, mean is equal to 0. But for height, do we have mean to be equal to 0? If the height mean is equal to 0, mean half the students should have height values below 0, minus. Do we ever have height values to be minus? No, all height values are positive. See? So then the question is that how do you get the probability? Now earlier we were using what? Table. And table is for what? Distribution, standard normal distribution. So that if you want probability for some other distribution, specifically, let's say standard normal, sorry, it's yet another normal distribution, but not the standard normal distribution. Then what we want is, we need to get the table constructed for that specific distribution. Now, standard normal distribution is specific distribution. Likewise, if you are interested for this ith one, then we need to construct the normal distribution for this distribution. This is mean height values for the mean, mu and then sigma. And if you can construct this table for this distribution, then using that table, we can find this probability directly. Now, this time is for height. Another person might be interested in weight, isn't it? Likewise, well, there is no end to this process. Variables, 1 million are interested in 1 billion different variables. So how many tables? 1 million tables. And then at some other time point, each is interested in some other variable. So how many tables you are talking about? Likewise, infinite number of tables. Is it possible? No, it's not possible. Infinite, not possible. So how do you handle this case? Right. People have found solution to this problem also. People have found that any normal distribution can be converted into standard normal distribution. Can be converted into Z distribution. So that once we have convert that into Z distribution, then using our Z table, we can find the probability. Isn't that great? Otherwise, infinite number of tables. Can you believe that? See the solution? How efficient it is. We can convert any normal distribution to standard normal distribution. And then once we convert that to standard normal distribution, we already have the solution. Solution is in the phone, isn't it? Because I have shared the table. So you can use that table and find the probability. So idea is this. X, I said 145. Which is 175. We are interested in 145, let's say. Probability X less than or equal to 145 is what we are interested in. So the idea is that this can be converted into standard normal distribution, so that for this 145, you find the corresponding Z value, let's say Z1. So that probability X less than or equal to 145 is equal to probability Z less than or equal to Z1. This is the solution. So Z1, once you know Z1, use the table. From the table you have, now we can find probability. So we have found the probability associated with X less than or equal to 145. Right. How do we convert X into Z? Z is given by X minus mu divided by sigma. Now for 145, Z1 is equal 145 mu. I said 175. See here, 175. Suppose sigma is 10. Which is minus 3. Therefore, so this is example. Therefore, probability x less than 145 is equal to probability z less than or equal to -3. For -3, you can find the probability from the table that I have given. By the way, that's the table. Yeah. 3 is this. Then this is +3. So that you subtract this value from 1 and thereby you get the appropriate probability. Okay. In fact, specifically wanted to show this. Now you see we have values, z value only up to 3.9. Suppose this calculated value was, suppose this calculated value was 5. Imagine this value is 5. Then how do you get the probability? Isn't it? Because this table gives only up to 3.99. Okay, 3.99, 0.9, 0.99997. Isn't it? So you can see how close it is to 1. So that 5 will be even closer to 1, but not much of a difference because this is already very, very close to 1. Okay. So that, well, suppose it is 5, obviously you can't find the value from this table. So that no harm going by this value. So during the examination, don't say that Z value 5 is not available in the table. You can go by this value, no problem. And then do the necessary calculation. Hope it is clear. Right. Now you see, what we discuss is given here also. So if we want to get minus value, then 1 minus probability z less than 1 minus z less than this z in terms of absolute value. Okay. Like minus 0.3, then you use 0.3 absolute value. Right? This vertical line indicates absolute value. Right. Okay. Hope now, according to this principle, you can calculate the probability associated with any x. Now, other way around is also possible. Probability x less than or equal to a is 0.3. How much is a? First, you find what? You find first probability z is less than equal to z1 is equal to 0.3. First, you find z1, and then once you have z1, you convert that into x. because Z1 is now X is minus mu divided by sigma, and thereby you can find X since mu and sigma are known. Okay. Similarly, you can have probability X greater than A less than equal to B is equal maybe 0.9. How much is A and how much is B? Should be able to find. So using the principle discussed earlier. Humans are is 145. Okay. Right. Example. Let X is distributed normally with mu and sigma square, where mu is 180. And I have taken an example. Do you want one more example? What is it? Same thing. Tumansa,
Yes, sir.
do you want another example? You mean for this one? Or what?
Yes, sir. Altogether, it's much better if you have one.
Nothing is now the. It's going to be. It's like this is 145 one. So we found that here we calculated this value, Z value, and from the Z value we found probability, didn't we? Okay, fine. Where mu is 180, and then sigma is say 20. Then question is that find probability X less than or equal to 160. Less than or equal to 160. Okay. Now thing is no table for this specific distribution. So first thing we need to do is to convert this into Z. Z is equal X minus, thank you. Okay. Z is equal X minus mu divided by sigma. Now X is how much? 160. Minus mu is given as 180. And then sigma is 20. How much is that? Minus 20 divided by 20, which is minus 1. So now we know, therefore, probability X less than or equal to 160 is equal to probability Z less than or equal to minus 1. Z less than or equal to minus 1. Yes. And we know, well, minus 1, if you first table you can use directly. Otherwise, from the second table, then what you need to do is work out this area greater than 1. which is 1 minus altogether. Right. So this is equal to 1 minus probability z less than 1. So this one table, it is indicated as absolute value of -1. And then 1 minus probability is less than 1. Probability is less than 1 is how much? Less than 1 is 1.0, 0.84134. Zero 0.84134, which is equal 66851. 0.15866 is the probability. Tumansa, is that okay?
Okay,
Tumansa?
sir.
Right.
Thank you.
Sir, excuse me, sir. Hello, sir.
Yeah, I can hear you.
Sir, when the equations are there, mu value and sigma value should be given, or is there any other theory to find that?
No?
According to the equation, is it equal to x minus mu and divided by sigma? In the equation, sigma and mu values are, we need to.
Yeah, you need that.
Yes.
It is like,
It's a normal equation. The value should be there, isn't it?
Which question?
Yes. Thank you, sir.
Yeah, this question, you see, mu is 180, sigma is 20. So these two have to be given. It is like, can we have a theory to find somebody's name? No.
Yeah, it's okay, sir.
It is like that. So we need to know. Likewise, mu and sigma should be given. Okay, right, good. What was the other question? Thing is that you won't be able to entertain. How do you find Z value when the probability equals 0.3 from standard table when we only have positive value starting from? That's what we were discussing. So you find the right hand side, corresponding right hand side. Point. What is this? Equals to 0.3. Plus 0.3. He said, so how do we find the Z value when the probability value is equal to 0.3? Okay. So from the P column, you find 0.3 and then read it onto the left.
Excuse me, sir.
Yeah.
Yeah, so in the table where we only have the positive values, it starts from 0.5, sir. But yeah, so that's what I.
Okay. So you can have a problem like.
Yeah, if we have the table.
Hang on.
Okay.
Now you can have case like, let's say, probability is at less than A is like 0.2.
Yes, sir. Yeah.
If it is like 0.2, as you know, we are talking about, because up to this point is 0.5. So it is 0.2 in sense that it has to be somewhere there. Then the Z value is minus.
Yes, sir.
Right?
Yeah.
So, I mean, the question can be turned around. Probability is less than or equal to A, 0.2, then probability is greater than probability Z. Now you see corresponding value,
Mhm.
corresponding value, you can work out to be what on the other side. From the other side, you find the value such that probability Z greater than B to be 0.2, isn't it? Because if this is what we are interested in A, but you can find value B such that this area is same as this area. So now the question is probability Z greater than B is equal 0.2. That this value can be found as the way we discussed.
Yes, sir.
Okay. So because then probability Z less than or equal to B is 0.8.
Yes, sir.
0.8 is a positive value.
Mm.
Okay. 0.8 is a positive value, so that you can find the positive value here, and then A is minus of that.
Yes, sir. Yeah. Okay, sir. Got it.
Okay, good.
Thank you,
Good.
sir.
Yeah, I think, yeah, when you start maybe working on homework only, you get stuck. That's right. Good that you asked that question. Was maybe another question? What was yeah, another question? A and B, I think that I did. A and B. Probability Z and less than equal to B is 0.8. So that probability Z less than equal to A is how much? 0.1. Because between A and B, 0.8. Outside A and B, 0.2. Half of that is on left-hand side. The other half, you find. We don't need music now. Maybe during the break, we can have some music. Yeah, probably message is that time to have a break, isn't it? Yeah, yeah. Good message. Okay, so we'll start from this point after the break. But I hope this part is okay now. Then probably goes A, B. This is 0.8. So that how much is this area? Is 0.1. So less than A is 0.5. So that you can find A. But A is a minus value. If it is Z, so that's right, this is Z. This is a minus value. And you need to work out as the way we discussed immediately before. Otherwise, in fact, if you use the first table, you can directly read that. Because in that table, minus values are also given. Okay. Right. Maybe I want to give a homework. Okay. Let's see whether this is the one. And one, let me find that and then give it to you. Right. Probably I will pass it to you after the break. So otherwise, you're wasting our time. Okay, right. So let's have a break and then meet after the break. Well, I think we have spent about 15 minutes for the break. So shall we start? Hope everybody's back after the tea. Right. Hope you everybody noticed that I have shared one document and it's for homework. Okay, so attend to that homework. It's about this. So it is this one I shared. Hope everybody can see that. Starting from Z values, finding corresponding probability values, and then given the p value, finding the Z value, and then given an interval, finding the probability. Sorry, yeah, that's right. Given the probability, finding an interval A and B, and then similar set of questions associated with a variable where variable is having a normal distribution, but not the standard normal distribution. Probability associated with the variable, and given the probability, finding kind of the corresponding x value, and then given the probability, finding an interval. Right. Third one, you can't answer immediately, but that's what we are going to discuss now. So it's all together. The question is, right. Well, so moving into what is indicated in the homework, bit about this Z transformation. I share the document. So talk to a person who goes around. Right. Now, imagine the case we are interested in something like what is that? Probability height less than equal to 160 and probability weight less than equal to 70 kilograms. Suppose this is what we need to compare. What we need to compare. The height less than equal to 160 and then weight less than equal to 70. Which value will be larger? Which value will be smaller? Difficult to judge, isn't it? Difficult to judge. Straight away, it's very difficult to judge. If you have the distribution, so this is the height one. Let's say mean is 170 and now one is 160 somewhere there. And the second one, weight, mean is, what is the mean? Let's say 65 is the mean. We are interested in, okay, let's say 80. Suppose mean is 80 and 70 is somewhere there. P1, P2. Right. If this line was on the other side, then you could have easily said that, okay, then P2 is larger than P1. But now, the value in the second graph as well as on the first graph, we find onto the left of the mean. See, onto the left of the mean. Because of that, it's very difficult to judge. Right. So if you want to go by the probability, now you see we need the corresponding two distributions, but as you know, tables are not available for those two. So in order to compare the probability, the only approach is first convert them into Z value, and then by means of Z value, you can find the probability. So Z1 is equal 160 minus 170 divided by, let's say, standard deviation this time is 15, and then standard deviation this time is 20, likewise. 160, 170, 50. And then Z2 is 70 minus 80 divided by 20. Okay. So this is what we have. Minus 10 divided by 15, and then minus 10 divided by 20. Minus 10 divided by 50 is 100. This is the 0.150 0.6, yeah, 667. And then this is minus 0.5, sorry, minus. So now we have the Z value, so that using the table, we can find the probability and then see that which probability is larger and which probability is small. You see, whenever you want to compare two variables, now this time I asked the exact question of probability. Now, similar question in a different way. Well, if you consider the case, having height value less than 160, and then having height value less than 70. Out of the two, is which one is less likely? Less likely. How do you find the answer? First, find the probability, isn't it? Less likely. Probability small means less likely. Probability large means more likely. Isn't it? Let's compare the probability. Right. Similarly, one student is having 80 marks. 80 marks for one subject. Another person is having 70 marks for another subject. Who is the better student? Or which one is less likely? Having 70 marks for second subject or having 80 marks subject 1 and then subject 2. One student is having, I said 80 marks. Another student having 70 marks. Which is less likely, and then which one is more likely? How do you find that? Or otherwise, who is the better student? Person with 80 marks or else person with 70 marks? Using the mark itself, you see first student is having a higher mark compared to second student, 80 and 70. Both are marked out of 100. So can we say first student is better than the second student? Student 1 and student 2. So can we say first student is better than the second student? You cannot say it. With the raw mark, you cannot say that. Right. Before discussing it further in this example, let's say I told a person that person is having a choice of 5 kilograms of iron and then 5 grams of gold. 5 kilograms of iron and then 5 grams of gold. Only one can be taken, not both. Which one will be selected? 5 kilograms of iron or there is 5 grams of gold? Utumansa, what do you prefer?
Exactly, it's a gold bar.
Yeah, that's right. Why gold?
Based on the value.
That's right. You see, you don't go by the weight. As Uttumansa said that, in real world, what we do is that, you see, what Uttumansa did was that he immediately converted that into what? rupees and cents, value. When we have the value for 5 kilograms of iron and value for 5 grams of gold. In terms of value, when you say value is value in sense that we have a common scale, isn't it? So that you can see which value is larger, which value is smaller. So that you can easily select the one that you want, the one that is having higher value. Isn't it? Otherwise, we don't go by weight. Isn't it? 5 kilograms is much larger than 5 grams. But we don't select 5 kilograms, isn't it? Because the weights, the two weights are not comparable. The two weights are not comparable. Why? The weight of iron and the weight of gold, two different variables, cannot directly be compared. Although weight we can have in kilograms, Now remember, earlier we were talking about weight and height. Can we have the same scale? No, we cannot have the same scale. We cannot have the same scale. So here, the gold and iron cannot directly be compared. You need to convert that into common scale. What is the common scale? It's a value in rupees and cents. Then you are in a position to compare the two and then say that which one is better than the other. Likewise, the two subjects, although we are talking about 0 to 100, thing is that two different variables, two different distributions. Because of that, the raw marks cannot directly be compared. It's like 5 grams of gold and then 5 kilograms of iron. Or it is like, let's say, 5 apples, and then 5 apples, and then 10 coconuts. 5 apples and 10 coconuts. What do you prefer? Just because we have 10 for coconuts, it doesn't mean that we are going to pick the 10 coconuts. What we do is, as Ottoman said, that we convert that into value. When you have value, you have common scale. Then you can say that which is better and then which is not better. Okay. So when it comes to marks also, what is the common scale? Common scale or the common platform. When we have a common platform, we can compare. So what is the common platform? See, you can convert both into what? Is it? We can convert both into Z. We can calculate Z1 for this subject. 80 minus mu divided by sigma. And then for the second subject also, we can calculate the Z score 70 minus, say, mu2 divided by sigma 2. When you have the two Z values, Z1 and Z2, then you are in a position to say which is better and which is not better. Which is more likely and which is less likely. Now, let's say first subject 80 marks, mean is 90. And then the second subject, mean is 60. Now, first student has got 80 marks. But that student is a below average person because average had been around 90. Can we call below average person to be a good student? Can we? No, I don't think so. Now, second one, mark wise small. mark-wise relatively small, or is smaller than 80, but the thing is that that person is, well, above average person. Above average person. Okay. So that we find second student to be better than the first student. But mark-wise, second student is having a lower mark compared to the first student. Not the same subject, two different subjects. See, marks across different subjects cannot directly be compared. Why? Two different distribution. Some subjects are relatively more difficult compared to some other subjects. But earlier, we did not take this into account. I think we said when we look at the averages, certain subjects we find that average to be like, let's say, but some extreme subjects, average is about 90. Religions, you see, languages, some, you find it be like averages are very high. Whereas subjects like, let's say, physics, you find average to be physics, or there's even mathematics, you find to be like average is very low. Right? So if the average is 40, now we can see having 60 marks, it's kind of, you are a great student, isn't it? Average is only 40, but I've got 60 marks, way above the average. Definitely a good student. Whereas, even if you have got 70 marks, 80 marks, if the average is about 90, 95, you are way below the average. See, raw marks cannot directly be compared. So using Z score only, it can directly be compared. So that you convert both into Z. It's an example, let's say, first one, Z1, 80 minus 90, suppose this is 10, and then Z2 also, let's say, 70 minus 60, and then 10. Here we are talking about -1, here we are talking about +1. Now you see, as I said, score, minus values are also possible. What does that indicate? Below the mean. Minus mean below the mean. Okay. So understand the concept. Whenever you have two different variables to be compared, cannot directly be compared because distributions are different. Okay, so you have a common platform. With a common platform only you can compare. So Z score is the common platform. So that's why for the university admission criterion, we use the Z score. Right, so that is a bit about Z score. Right. We're talking about probability associated with variables. But when it comes to making decisions, obviously, we don't go by an observation. We don't go by an observation. But we definitely go by estimates such as sample mean. Estimates such as sample mean. So that we could be interested in probability associated with, let's say, sample mean. Probability associated with sample mean. Now earlier, when we want probability associated with X, what did we discuss? Distribution of X. Distribution of X. Mu and sigma. So that if you are interested in probability associated with sample means, what we want is distribution of means. Distribution of means. Then only we can have an understanding about probability associated with sample mean value. So now the question is that, how do you have the distribution of means? Right, now as well, distribution of X, I said, usually for a continuous variable, we find it to be normal, isn't it? So now the question is that, how do we have the sample mean distribution? How do you have the sample mean distribution? Now, what do you mean by sample mean distribution? Let's say this is the population where the mean is mu and then standard deviation is sigma. We're taking a sample. So when we have a sample, of course, we can calculate sample mean. Suppose we took another sample. Do you think that sample will also have the same mean? No, it's a different mean. So we can call this to be x1 bar and then this to be x2 bar. Likewise, when you go on picking samples, you find that sample to sample, sample mean is different. So we have to come about now large number of sample mean values. So we can think of distribution of sample mean values. Exactly. Same population. Distribution of sample mean values. This is what is called sample mean distribution. Often called sampling distribution. Sample mean distribution, otherwise sampling distribution. Right. Now, what kind of distribution do we have for sample means? Now you see, according to the distribution of the population, we find most of the values to be around the mean, isn't it? Most of the values to be around the mean. So that when we pick a sample randomly, where do we get most of the values for the sample? Let me say that again. We find most of the values to be around this place, around the mean. And when we pick a sample randomly, where do we get most of the values from? Then obviously when most of the values are around the center, when we pick observation into sample randomly, most of the time we will be having observation from this area because most of the values are in that area. So that when we pick some into a sample, obviously we will have most of the values into sample from this area. So when we have a sample from this area, what can I say about the mean? Mean will also be from this area. So that most of the time we will have mean from this area, and well, with few times you will find mean to be from this area. Because of that, the sample mean also we will have distribution like this. Pretty much same as this. Got it? Because most of the values are from this area, so sample mean will also be from this area. So most of the time sample mean will be from this area. Because of that, you will have higher frequency for sample means from this area, and then, well, less frequency for sample means from this area, or those values. Because of that, you will find shape of the distribution is pretty much same as this distribution. Meaning, sample mean will also have the normal distribution. If it is normal distribution, then we are talking about what? Right in the middle, mean. That is mean of the sample means. And then spread is given by sigma x bar, or that's variance of the sample means. Mean of the sample means, mean of the sample means. And then variance of the sample means. In fact, it's quite interesting. Good old days. Good old days. There was famous theory called central limit theorem. Central limit theorem. And then, according to this theorem, whatever the distribution you have for the population, suppose this is the kind of a distribution, highly weird, isn't it? It's a weird distribution. Thing is that when you pick samples from this population, sample means will have normal distribution. Can we call this to be normal? No way. No way. Well, first of all, it has to be symmetric, isn't it? It is symmetric. Come on, how can you call this to be symmetric? See, it's like several modes are there. Not just one mode, but normal distribution, only one mode is there. But interestingly, sample means when you have samples from this population, sample means will follow the normal distribution. That is what the central limit theorem says. But in fact, there's a clause sense that sample means will follow the normal distribution with mu x bar and then sigma square x bar when n is large. That's important. N is large. Sample size is large. Okay. Sample size required varies depending on how deviated the original distribution from the normal distribution. If the original distribution is highly deviated from the normal distribution, then the sample size required for the sample mean to follow the normal distribution is large. If the original distribution is pretty close to the normal distribution, even with small sample size, you can have sample mean to follow the normal distribution. So that is what it says, with the increase of n. But now this theorem is not that actively used, but not that we don't use it at all. In fact, you will see, especially when it comes to certain specific situation, we use that. Okay. But now it's like less and less use because we don't want to worry about the distribution. Now, well, whatever the distribution, we just go by existing distribution. We don't worry about whether the distribution is normal or not. Okay. Right. So this is what the central limit theorem says. But the thing is that when original distribution is normal, definitely you find sample mean also to follow the normal distribution. And now you know the reason behind that. So that if the interest is like x bar less than or equal to some value, say 80. So what we want is then the distribution of sample means. Right? So you are interested in, if it is normal, interested in mu x bar and then sigma square x bar. Right. Now, think of a case, population consists of 1, 2, and 3. This is the population. Mu is equal to how much? 2. Now, let's think of taking samples from this population. Samples of this population. The only possible size for the sample is n is equal to. How about n is equal to 1? No, it's one observation. You don't call one observation as sample. It is just an observation. And n is equal to 3 is not a sample anymore. It's a whole population. Isn't it? So that these two are out. So that only possible sample size is n is equal to. So with n is equal to, what are the possible samples? Possible samples 1 and 2, 1 and 3, 2 and 3. And what are the sample means? 1 and 2, 1.5. 1 and 3, 2.0. 2.3, 2.5. Isn't it? Therefore, mean of the sample means. Now we have considered all possible samples. That's why I am using mu. Mean of x bar is adding all three, 5 and 5. 1 left, 2, 4, 6, 6.0 divided by 3, which is equal to 2. Is that interesting? Isn't that interesting in sense? In sense, mu x bar is equal to mu. Mean of the sample means if you consider all possible samples, then you find mean of the sample mean to be exactly same as the population. This is always the case. But remember, you need to consider all possible samples. Now maybe as homework, you can try values 1 to 5. Maybe think of samples of size 3. Like 1, 2, 3, 1, 2, 4. Likewise, think of all possible samples. Get the mean. 2, 3, 4, 7, 2.33. Likewise, get the, and then mean, of course. You will see mu x bar is equal to mu. Right. And consider population 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Larger than the previous one, isn't it? Previous one we had only 3 values, but now we have 10 values. Right. This time, now what is the other parameter that we are interested in? Is a variance. Mu, because normal distribution, how many parameters? 2 parameters. Don't forget that. Normal distribution has 2 parameters. Once you know those 2 parameters mean we know the whole distribution. See the advantage of having a distribution sense that once you know the parameters of the distribution, if you know the distribution in sense that all what you need to know are the parameters of the distribution. Once you know the parameters mean whole distribution is described. Then now we see y is equal mx plus c. Y is equal mx plus c. Given m and c are the parameters. Given m and c, for any x value on this earth, you can calculate the y value. Is that interesting? For any x value on this earth, you can calculate the y value. All what you want are m and c. Just those 2 values. See, this is the usefulness of parameters of the distribution. And this is the usefulness of having a distribution. See, you are in a position to do a lot of calculations based on that. See, once you know the distribution, it means that once you know the parameters, now you see, we were calculating probability associated with any x value. You can do that since there is a specific distribution for the variable verb. We were talking about the normal distribution. So that is the advantage of having a distribution. Some variables, maybe not in this course, you find that you can't think of an exact distribution. Such a case, calculating probability associated with the value, oh, very difficult. Very difficult. So, well, it's not as simple as this is that every time you need to have values. Now, see, in the homework, what I gave was that mean and then the variance. After that, I gave what's it called? Find the probability associated with 30, probability associated with 59, probability associated with 89, likewise. See, for any value, we can calculate the probability. Because once the parameters are given, all distribution is described. But if you cannot assume that kind of distribution, then you find it to be like every time you need to have data. Using the data only, we can estimate. Okay, right. Right, so let's say we have 10 values. Now the interest is what? Variance. Calculating variance is not very straightforward, is it? Because remember the formula? Sums of square divided by the degree of freedom, degrees of freedom. Okay, so not very straightforward. But an easy measure is range. Remember, range. One thing we know, range is easier to calculate compared to variance. Range is also a measure of what? Dispersion or the variability. Right. And the other thing what we know is that if the range is large, variance will also be large. If the range is small, variance will also be small. That we know. Range is not exactly equal to the variance. But the thing is, if the range is large, variance will also be large. If the range is small, variance will also be small. That we know. So let's calculate range and then using which try to get an understanding about the variance. Now let's calculate the variance, range for the population is 9. 10 minus 1 is 9. Now imagine taking samples from this population. N is equal to, what are the smallest values possible for the sample? Is 1 and 2. What are the largest values possible for the sample? 9 and 10. If it is 1 and 2, sample mean is 1.5. If it is 9 and 10, sample mean is 9.5. You cannot have the mean of the sample to be outside 1.5 and 9.5. Isn't it? Smallest sample mean possible is 1.5. Largest sample mean possible is 9.5. So with this, you find range to be equal to 8. Can we ever have range of the sample means to be larger than 8? No, not possible. Not possible. It's not possible. Right. Now, see what has happened. From 9 to 8, it has decreased. Range has decreased. What does that mean? Dispersion is more. Dispersion is less. For the sample mean, or the variability is less for the sample means compared to the population. So the variance is always smaller sample means compared to the population. Not like the mean. Now you see, earlier we found that mean of the sample means to be exactly same as the mean of the population. But variance, no, it's not same. It's not same. Variance of the sample mean is always smaller than variance of the population. Okay. Let's consider n is equal to 3. N is equal to 3. What is happening? If n is equal to 3, just a minute. N is equal to 3. Now, what are the smallest values possible? 1, 2, and 3. Mean is equal to. Largest values possible 8, 9, and 10. What is the mean? 9. Now, how much is the range? Range is equal 7. Now, what can you say? Well, still you find that range to be smaller than the population. Yeah, that's very clear. I suppose, that you can understand from the previous case with n is equal to. Right, so no wonder with n is equal 3, still the range is smaller. Nothing to be surprised. But from n is equal 2 to n is equal 3, what do you find? Range has become smaller. From sample size 2 to sample size 3, the range has decreased. So the range is smaller. Meaning what? Now the first concept that we built was that variance of the sample mean is always smaller than first one is sigma square x bar. Variance of the sample mean is always smaller than variance of the population. And what is the second one we are telling that? Sigma square x bar decreases with the increase of sample size. Or otherwise, when n increases, sigma square x bar decreases. That's how we find it. Okay. In fact, you find sigma square x bar to be sigma square divided by n. I think this tallies with what we discussed in it. Sigma square x bar is always smaller than sigma square. Why? Sigma square divided by n. N is always larger than 1. Isn't it? N is always larger than 1. So that sigma square x bar is always smaller than sigma square. That's 1. And then with the increase of n, you can see sigma square x bar decreases. Okay. Right. Now you see, with respect to mean, I showed you mu x bar is equal to mu. Using an example, we verified. But sigma square x bar, I'm not going to verify. Well, you can try that. Now see, possible samples, maybe with 10, large number of samples are there, but you see, with 3 samples, you can try that. Sorry, with 3 observations, sample size 2, previous one. With that, you can calculate. The variance of the sample means. You can calculate the variance sample means. And then see that whether it is equal to sigma square divided by n. You will find the two values are not exactly the same. Not exactly the same. The reason is that there is another factor coming in. Maybe we don't discuss that in this course. But well, those who follow the course in sampling, remember I said that we have kind of complete separate course offered in sampling. So there you will get into the details. I'm sure you will talk about this aspect also. Now what I'm telling is sigma square. This is not exactly the same. Sigma square x bar is approximately equal to sigma square divided by n. Okay, very, very close, but not exactly the same. To be exactly the same, you will find there's another factor coming in. But we don't discuss that. The reason is that if capital N is large and simple N is small, this factor is almost equal to 1. Equal to 1. But not exactly equal to 1, approximately equal to, almost equal to 1. So this is almost equal to 1 in the sense that it is like what? Sigma square divided by N. Okay. So when you try that after going home, you will see that two values are not exactly the same, but very close. Okay, because of that factor. But well, for this course, we take that factor to be 1, because when N is large, when capital N is large and simple N is relatively small, you will find that factor to be almost like 1. But keep that in mind. In case if you take samples with replacement, put that value back into the box. So it's possible you get the same value. It's like previous example, 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, 2 and 3. See, it's possible same value again. In such a case, you find sigma square x bar to be exactly equal to sigma square divided by N. Otherwise, there is another factor coming in. Okay. But for this course, well, good enough. Just use this. Say this is the first course. Okay. Right. Now we have got the distribution sorted out. Right. X bar distribution, mean of x bar, which is equal to mean, and then sigma square x bar, which is equal to sigma square divided by N. So that we are in a position to calculate the probability associated with it. Right. So when the question is probability x bar less than or equal to A, first thing is we need to convert this into probability Z less than or equal to simple Z. Where simple Z is given by what? Remember, Z is x minus mu divided by sigma. It's the general transformation. But now the x value here is an x bar value. So that Z is general case x bar minus mu. What is mu? Mu is a mean of x. So that we want mean of x bar. And what is sigma? Sigma is standard deviation of x. So now in the place of x, what we have x bar. So that's sigma x bar. Is it? Sigma x bar. And we know mu x bar is equal to mu. According to the findings that we made, x bar is, mean of x bar is equal to mu. And then sigma x bar is equal to sigma square divided by N square root. Okay. So that we have the Z value. Once we have the Z value, is dead easy, isn't it? Just refer to the table and then find the probability. Okay. Right. So this is how we deal with probability associated with sample means. So that if I give a question like x is distributed normally with mu, say 100, and then variance 225. Now you see, this is how it is usually indicated. What is N stand for? Normally. And what is this? Is about distribution. Distributed. And then two values are there. Why two values are there? because normal distribution has two parameters. Two parameters. And first one is mu, second one is variance. And when it is given, you can calculate mu x bar as well as sigma square x bar. And then once you have those two values, mu x bar exactly same as mu. So substitute this in this equation and thereby you can calculate Z. Once you have Z, you can find P. Isn't it? Right. I think now you can answer to the last three questions in that handout. Sorry, the document I shared you, homework or the tutorial. So now you can answer to the last three questions. Okay. Probability associated with sample mean value. And then given the probability, finding the corresponding sample mean value. And then given probability, finding an interval of the sample mean values. So all that you can do as the way you answered to the previous 6 questions. Sigma square x bar is what variance of the sample means of x bar. Okay. The square root of sigma square x bar is sigma x bar is called standard error. Standard deviation of sample means variance of x bar, square root of that is standard deviation of sample means. But it is often termed as standard error. Standard error. Why do we call it standard error? Now you see, this is nothing but standard deviation of sample means. Standard deviation of sample means. Right. Standard deviation. What is the standard deviation? What do you mean by standard deviation? Is on average deviation of an observation from the mean. Isn't it? That's how we define standard deviation. Now, what values are we talking about? Sample mean values. So this can be interpreted as what? On average deviation of a sample mean from the population mean. Isn't it? On average deviation of a sample mean from the population mean. Now, what is sample mean relative to population mean? Sample mean is the estimator of the population mean. Sample mean, once we have the value, it becomes an estimate of the population mean. That's an estimate. But we know sample mean will never be equal to the population mean. There is always a difference. There is always a difference. That difference is termed as sampling error. I think some other day also we discussed this. Sampling error. See, that difference is termed as sampling error. Nothing wrong with that. This difference is termed as sampling error. Since what we are aiming at the population mean, this difference is termed as kind of an error. Because of studying by means of sample, the error that we come across. See, on average deviation of sample mean from the population mean. See, because of the population mean is a target in sampling, and then sample mean will always be different from population mean. This standard deviation of the sample mean is termed as standard error. The deviation is kind of can be considered as an error, or it is often termed as error. Because of that, standard deviation of sample mean is termed as standard error. Okay. On average deviation of sample mean, not observation, sample mean from the population. So that's how it is called standard error. Right. Now this standard error, sigma square x bar, and then n. What is happening to standard error? It decreases in it. You will find it to be of this form, because sigma square divided by n. Sigma square is a constant, isn't it? With the increase of n, we can see it's continuously decreasing. So you will find the graph to be of this form. So now see sigma square x bar. Sigma square x bar. It depends on what? Sample size. Isn't that interesting? Meaning sigma square x bar can be manipulated. Can be manipulated. So if you have sample of the size somewhere there, this is going to be the standard error. But if we use sample of size this much, then it's going to be only this much. Exactly. So then if we want, we can make standard error to be large. If we want, we can make the standard error to be small. We can make it. But can we manipulate standard deviation of variance of the population? No. Now remember, yesterday you were talking about that homework. I hope some attended that homework. By the way, Uthuman sir, how many values were there?
So I think only 38 values, sir.
Only 38 values. Why? What happened? Kamal, did you submit your value?
Yes, I submit.
You submitted. But still only 80. How about Gamage? Did you submit your value? Gamage?
Yes, I submitted
Oh,
my
really?
value.
All right. And then did you work that out? Did you do the homework, Gamage?
Yes, sir, up to standard deviation
Based on how many values?
based on 38,
38. Uthuman sir?
37.
37. Okay. But how come you see in the class we have 131? Buddhika? Somebody's talking. Who's
Yes, sir. Even it's not allowing me to submit the value, sir.
what? The Google sheet?
Yes, sir. Good. Excel sheet. Yes.
Yeah, true. But thing is that, how come no access to submit your value? That's not possible. Is anybody else having that problem?
Yes, sir. Me too have that problem.
Oh, really?
It's give the permission views only, not for edits.
I don't know whether it was kind of identified for a specific period, so that from that point onward, you cannot add values. But anyway, I will check with our computer unit, the PJIJ, and then see, what has gone wrong. Anybody else kind of, let's say, Vimala Singha, PDN, sorry, no, not PDN. Vimala Singha,
Yes, sir.
did you attend to that homework?
Not yet, sir. But
Okay.
today I got the values from
You are
Excel.
busy. Maybe you were busy. Huh? Okay. How about Purnima? Purnima,
Yes, sir. I
how about
also
you?
can't enter the value, sir.
You also didn't enter or you could not? No permission.
No permission, sir.
When did you try? Was it yesterday?
No, sir, last week.
Last week also you had that problem.
Yes, sir, yeah.
How come you didn't tell me that yesterday?
Yeah, I thought wait and see today also, sir.
Where the permission is granted.
Yeah.
Interesting. Huh? But the thing is that it's supposed to be from the beginning that the permission is granted. Thing is that whenever you have an issue, when if somebody is having an issue, you should tell me so that you can attend. I can attend to that. Right. Okay.
Sir,
Yes.
sir, when I tried to add the height data into the stem and left plot, there are 3 decimal points out of 38.
3 decimal points.
Yes, sir. So how to add in that stem and leaf plot, sir?
Did you attend
Example,
to
sir,
our...
152.4.
That's right. I understood the question. Thing is that, did you attend to first few meetings?
Yes, sir.
Join the class, huh?
Yes.
You did?
Yes, sir.
But remember, we discussed, how to handle decimal values.
Yes, sir. But
Large
here
numbers.
this decimal is variable and normal point is where we can
Right.
do.
So remember, our principle was that when values are large, like 185, so then it doesn't really matter whether it is 185 or 185.3. So that we ignore that 0.3 and then go by 185. That is the idea. Okay. So we discussed that under the concept of like dealing with large numbers. When you have, say, 140, 230, 650, likewise, then what we said is that we take 100 as a stem unit and then 10 as a leaf unit, so that you won't be able to distinguish 124 from 129. We discussed that. So likewise, when you have the values in especially centimeters, since the values are large, then you can forget about like 128.3, 128.9. You take both values as 128. Okay, so that is how you handle that. Is that clear?
Okay.
Sir, I'm Aziz.
Aziz, yes. Yeah, I think you were the one who logged in yesterday through that iPhone and then was asking you to add the number. You have added that. Good. Yes, Aziz. Yes.
Sir, what homeworks I don't, because I didn't participate there before class.
Which class? You mean today?
No, sir. Before 2 or 3 classes, I didn't participate, sir.
Okay. So are you talking about these height values?
Yes, yes.
Shall I tell you? I think when did I? No, I think it was maybe last week Sunday. We did that. Last week Sunday. Did you attend that meeting?
No, sir, I didn't, sir.
Did you start from yesterday?
Yes, yes, sir.
Okay. Maybe then thing is that you need to talk to somebody, who is having access. But I think it's in the Google Sheet. Since you have got the drive, check the chat box.
Okay, sir.
Check the chat box, and then the Google link is there. So with that, you can have access. Anybody can have access.
Okay, sir.
Right. Let's move on.
Sir, but the problem is this, I am unable to edit this. Like even last week, I couldn't even enter the values.
Yeah, that is what some others were also telling. Is
Like
that
if I,
that permission not granted or what?
yes, the permission is not granted. You can only view it. So even if I download it and I put the values, where am I supposed to upload that file?
No. You okay. Well, once you open that, well, you should be able to kind of enter your value directly without any problem.
Yeah, directly,
Regular
right?
Google
So
Sheet,
there is an option of download. So once you
Ah.
download it, it comes into your system. So you are able to edit it. This is what I'm trying to say.
Yeah, but right, that's fine. But now looks like problem is you cannot enter values.
Yes,
Isn't it?
exactly.
That's why I said that. Well, I will inform that to the PGIA computer unit, and then see, ask them to check, what has gone wrong.
Okay.
Okay,
Okay,
right.
thank you.
Let's move on. What were we talking about? How come, we came into slide 1 message? What is it? What is it? I mean the values. Okay, right, whatever. Probably now Tumansa has shared those values so that maybe you want one can use those values also and then do the calculation. But anyway, I will ask PGIA to enable that so that everybody can enter those values so that you will have more values. Now, Bandara has also, is it those height values? Maybe, no. Okay. So now, in case, if there's a problem, well, one can use these values and then do the homework. Okay, otherwise, if that matter is sorted out, you can use those values. Okay, right. Let's move on. So, you have sample size of like 30. Now the thing is, if you have the sample, now according to this, when the sample size increases, you find that variance to be decreasing. Now the population variance that you calculated, height values, can we change that height, the variance? How can we change the variance? Variance cannot be changed. We want to change the variance, we need to change the height values of students. Can we change the height values of the students? How can I change height values of the students? Remove the height values of tall students and then add those height values to those who are not very tall. Is it possible? No, how come? It is possible. That is not possible. So that you can see variance of a variable or the variability of a variable is inherent. That cannot be changed. But variance of the sample mean can be changed. See, according to this graph, you can clearly see that variance of the sample mean can be changed. Now remember, we discussed maybe on the very first day, what we want is sample mean to be precise. Isn't it? Less variability from one sample to the other. I think now you can understand how we can make it precise. Isn't it? Once we have the sample size to be large, you see somewhere there, variance is only this much, very less. Isn't it? Very less sample size somewhere there. This sample size, say N1, variance is only this much. Small variances, so from one sample to the other, you will find the difference is small. But if you're using sample size of something like this much, then you can see that substantially high variability is there. So that you will find relatively large difference between sample mean values. Okay. So that with this, you will have less precision, but with this, you will have high precision. So the question now is that what sample size should we use? I think on the other day also I said that, well, there are formulas using which you can calculate sample size, but this is one approach that can be used and then decide the appropriate sample size. Okay. You construct this graph and then you can find a point. It's like beyond which, well, not much of a decrease is there. Not much of a decrease is there. See, from there to there. And then if you think of the same distance from there to there, let's say this is D. And here also D. See, for this D, decrease is like here D, this much of a decrease is there. But here, decrease is hardly any decrease is there. So that no point increasing the sample size beyond kind of this point. So that we can use this as the sample size. Thing is, when you undertake the study, it's very important you justify whatever you do. The sample size has to be justified. Otherwise, when you do the presentation, you can see so many questions are there. You can use a formula, then do the calculation. But the thing is that the questions you will have of the form, according to their experience, you see sample size cannot be of this much, it has to be much larger than that, and blah, blah, blah. So that it's good that you check with the other people what sample sizes that they have used. So the value that you got through the calculation should be pretty close to what other people have used. You see, if you can tell that, this journal article specifies sample size to be close to your one. And then another journal article specifies sample size to be close to your one. When you justify your sample size by that way, then you can see nobody can raise any question. Otherwise, one can suspect your calculation of sample size and then wrong information used to calculate that sample size likewise. Okay, right. Now, for instance, how do you construct this curve? Now, see, using this curve, deciding sample size, how do you construct this curve? In order to construct a curve, obviously, you need to have several values. One study, you will have only one value. So, how do you have several values? This is where it says you need to have a good literature survey. Once you go through the literature survey, you can see that for each article you have a separate value. If you go through 10 articles, mean 10 different values. Then you are in a position to construct this curve. Because everybody is mentioning about the sample size and the variance. So that you can construct this graph. Okay, don't think you are the only one who is doing research on this earth. Millions of millions people undertake research. So that information is available. So use that information and thereby you can work out something like this. From this, you can work out what sample size you should use for your study. Okay. So that's a bit about standard error. I think with that, we can conclude discussing about probability. Now, see, first we started with discrete case, and then we moved into continuous case. Okay. By now, you should be able to deal with any variable, regardless of whether it is discrete or otherwise continuous. Okay. Right. Let's move into a new topic. Hypothesis testing. Hypothesis testing. Hypothesis testing, anybody can understand. Hypothesis, I'm sure, from the school time, you have come across hypothesis. So, hypothesis, what is it? It's the starting point of research, isn't it? Any research, you have to have a hypothesis. Without a hypothesis, you can't undertake a research. Starting point. Well, maybe as close words to hypothesis. It's like maybe like what you believe in. You think something happens because of you think because of a specific reason. Right, let's say when you keep a plant next to a window, you can see that, after several days, that top of that plant turns into outside. It is bending towards outside. So now, to begin with, it wasn't like that. I think very first day you didn't see it that way, but you see after a few days, now you find it to be like the top is kind of turned towards outside. Now you start thinking of how come with that, the reason behind that, you see. So you come up with like different reasons. This one is very straightforward, it's well established, the reason. But you see, likewise, sometimes the information is not established. So you start thinking, it could be due to this. That is what is called the hypothesis. And then you, if you are kind of convinced, then you start strongly believing that. That's why I said that maybe a close word is believe. What do you mean by sample error? No, there is nothing called sample error. It's like you have made a mistake with the sample. Okay, it's not sample error. We are talking about standard error. Standard error is nothing but standard deviation of the sample mean distribution. Right. Back to the topic, hypothesis testing. What you think of the reason is what is called the hypothesis. But what you think, could be wrong. Okay. So two possibilities are there. Either it is correct, or your hypothesis is correct, or otherwise your hypothesis is wrong. That the hypotheses are always correct. Sometimes you find hypothesis to be wrong. How do you know that? This is where you need to conduct the experiment or the study. After the study, within the study, what is happening is that we are performing tests. That is what is called hypothesis testing. After the study, once you complete this testing, then you will understand what we thought is correct or wrong. Whether the hypothesis is correct or wrong. At that time only you will know that. Okay. Until then, well, both possibilities are there. Either correct or always wrong. Right. So this is about the term hypothesis. When it comes to hypothesis testing, we define two forms of hypothesis. Two forms of hypothesis. One is called null hypothesis. And the other one is alternative hypothesis. Null hypothesis and alternative hypothesis. Null hypothesis usually denoted as H0, H0, H0. Alternative hypothesis is denoted as H1 or otherwise HA, A for alternative. Interestingly, HA is opposite of H0. Or as H0 is opposite of HA. That's how we have. So, if you can formulate H0, HA is very straightforward. Or if you can formulate HA, straightforward to have H0. Well, it's opposite. So, one might have a question now, which one do we formulate first? Sometimes people go by like H0 followed by HA, or sometimes HA followed by H0. Conventionally, it is H0 followed by HA, conventionally. But nothing wrong. Some studies you find it to be like HA can easily work out, and then opposite is H0. But in general, H0 is nothing but reference value. H0 is nothing but a reference value. Well, as you know, in day-to-day life also we say that you have to start from somewhere. Isn't it? You have to start from somewhere. See, if you want to achieve something, you need to start. See, without starting, how can you help? You need to start. You start working. And where do you start? Where do we start from? What is the starting point? Okay. That is what is called reference value. Reference value. And then once you formulate that, well, opposite is taken as the alternative. Opposite is taken as the alternative. And thereby you have the two. And very often you find that alternative is your general hypothesis. Now remember I said that you need to have hypothesis. Plant is turning due to this. That's your hypothesis. But based on that, you define two forms of hypothesis called null and alternative. And then very often you find this. The form that you identify as alternative is what you had as your hypothesis. Let's take an example. Simple example. I often take the example of tossing a suspicious coin. Suspicious coin. What do you mean by suspicious? Looks like it is not normal. Looks like it's not a normal coin. What do you mean by normal coin? Doesn't mean that suspicious coin has 3 sides or something. No, still that is also having 2 sides. Otherwise, how can you call it as a point? Yeah, 2 sides are there. So what do you mean by normal point and not normal point? We know, but the probability of observing head on a normal point is what? Half. So if the probability of observing head is different from half, then we can call it to be not normal. Right. Now we are talking about suspicious coin. Looks like when you're tossing, you found it to be like behaving differently. So you start suspecting. See? Suspecting in the sense that now your belief is that this coin is not normal, isn't it? That's why you have started suspecting. So the coin is not normal is what your guess now is that coin is not normal. So that is like what you want to study, that is your hypothesis. Now we need to formulate the null hypothesis and alternative hypothesis. Now, normal is what? P is equal half. Normal is probability of observing it is half. If it is different from half, we call it the coin is not normal. Right. Now the question is what is the null hypothesis and what is the alternative hypothesis? Right. Now recall that null is what? It's a reference value. Null is a reference value. When it comes to probability of observing head, what is the reference? What kind of values do we use as reference values? Established value model is not well established values. It's established values. So now the question is that when it comes to probability of observing head, what is the established value? Probability of observing him for a normal coin is established. What is that value? Half. That value is established. Of course, we are talking about suspicious coin. So one might think of, okay, like 0.6, 0.7, or 0.3, according to your suspicion. Likewise. Then one can question like, why exactly 0.6? Why not 0.65? Why not 0.62? Why 0.7? So this is where we usually have reference value, established value. It's defined. So we can define then H naught as what? P is equal half. Because that is established value. And since it is established, we can use as a reference so that it becomes what? The null hypothesis for the study. Now, is that interesting? What do you mean P is equal half? P is equal half means the coin is normal. When you say P is equal half, its coin is normal. But what you are studying is what? Suspicious coin. But starting point is what? The starting point is what? This coin is also normal. And then what we do is we study the coin. We make observations and then see what the outcome is going to be at the end. Right. Now the starting point is what? Coin is normal. And what is alternative? Is that it's opposite. Opposite. So that HA is what? P is not equal to half. See? I think now you can understand. Now you can see that. I said, usually your general hypothesis becomes what? Alternative hypothesis. Because you are suspecting. expecting instant that this coin is not normal. What do you mean not normal? Probability of observing it cannot be half. Okay. So now we have formulated null hypothesis and alternative hypothesis, and this is how we usually formulate null hypothesis and alternative hypothesis run experiment or let's start. Okay, so null hypothesis is nothing but reference, and then null and alternative are the two forms opposite to each other. So in this case, you can see, in fact, if you formulate the alternative, then you can think of other way around also, isn't it? From alternative also, you can formulate null. That's also there. So that's why I said that sometimes people go by like null followed by alternative, and sometimes you find that alternative followed by null. Now we are studying that coin. How do you study coin? You toss it for some time and then see that how many heads that you get. Why? If it is a normal coin, we know probability of observing head is half, so that half the time we expect outcome to be head, and the balance half the time we expect right, the balance half the time, we expect the outcome to be tail. Isn't it? But just think of reality. I suppose some of you have tried this. Tossing a coin 50 times. Just imagine normal coin. Just took it from your wallet or the purse and you toss it 50 times. Normal coin. Okay. Do you think you will get exactly 25 heads and 25 tails? No. You will not get exactly 25 heads and 25 tails. You can easily have value like 23 heads and 27 tails. Or otherwise 24 heads and 26 tails, or otherwise 22 tails and 28 heads like that. That's how you see. I don't think you will ever come across exactly 25 heads and 25 tails. Okay. How come sometime it is 23 times 23 heads and 27 tails, and then the other time it is 24 heads and 26 tails? What is the reason behind that? Cannot be explained. Cannot be explained. This is what is called random variability. Random node, you can't think of a reason. Same place we are talking about, same coin we are talking about. So this is what is called random variability. You come to a point that certain variability cannot be explained. This is what we termed as random variability, or sometimes we call that as error. Nothing wrong with that. It's what is called the error. Otherwise, better word is what? Random variability. Otherwise, one can take it as something wrong. No, there's nothing wrong. You find that to be the case. Right, okay, back to the point. You will have values such as, 22 heads and 28 tails likewise. Okay. Now, isn't that interesting? From a normal coin also we find that we cannot get exactly 25 heads and 25 tails. Now, from unusual coin, anyway we cannot get 25 heads and 25 tails. So now the question is that how can we distinguish a normal coin from an unusual coin? Not normal coin. Because if normal coin gives always 25 and 25 and other coins give different from 25 and 25, then straight away we can say that, okay, well, this coin is normal, this coin is not normal. But the thing is that from a normal coin also, we don't get exactly 25 and 25. So the question now is that, then how can we distinguish normal coin from a not normal coin? Because from a not normal coin, anyway we will have values different from 25 and 25. Isn't it? Right. Now we need to answer that question. But I think we are getting close also to our closing time. So before that, shall we have the quiz for the day? Today we started, I think, about 6 minutes behind. So shall we then have the quiz? Can everybody get ready? Javadana, you can't talk to anybody. Who are you talking to? Ask others to be not around. Huh? Anura, hold the computer screen bit away from you. Bit more, bit more. I think now it is okay. Yeah, now we can see you. Is everybody okay?
Recording in progress.
Madhusha, I can't see you on the screen. Madhusha, maybe Madhusha is not around, no? Okay, fine. Shall we finish the quiz before the final exam? Then we will have the final exam. Masahir, can't see you. Masahiro ABM or 2272. Aren't you around? No. 2346. No. Danish. Shankar Harshani. Danesh, yeah, what is happening? Danesha, you have raised your hand.
2346, both are same.
2346 and?
Aziz also. Both phone and computer.
Okay. This thing, okay, that's why 2346, you can add that your name also, Aziz also. Isanka. Sejana.
Yes, sir.
Sanka, we couldn't see you earlier on the screen.
My laptop cam is not working.
Who is talking? Sanka or Sanka Harshani or who is talking?
Sijana.
Sijana. Thing is, where is Sijana? No, thing is, Sijana, examination, you can't give it that excuse, and then starting from next one, make sure it works. Okay?
Okay, sir.
Balasuri, sorry, Jayasuriya, RMIDB Jayasuriya. No? Right. So I don't expect answers from those. Right. Maybe a question based on what we discussed. Probability X less than 60 and probability X bar less than 60. Two probabilities. Consider these two probabilities. Compare the two probabilities. Compare the two probabilities. Mean which probability is larger, which probability is smaller, and then a reason behind that, maybe with 1 or 2 words. Don't write stories. With 1 or 2 words, justify your answer. You actually don't need, but maybe have an understanding about mu is say mu is 50 and then sigma is 10, something like that. Okay. With these two, I think you can have your answer much quicker. Okay. Well, cannot be difficult. As you know, whenever it is probability, what is the value you need to calculate first? Z value. Just think of, calculating Z value. Just think of calculating the Z value. You don't need the exact Z value, but you know how to calculate. So based on how to calculate, you can decide which probability is larger, which probability is smaller. So don't make it difficult. Okay, simple questions, don't think them in a difficult form. Now you see, I have given the answer. So by the way, send the answer quickly because otherwise you are getting late for the other course. You are starting that one at 1 o'clock. You will have no time for lunch. Now you have taken more than 10 minutes. By the way, make sure everybody sends the answer. I don't know whether I mentioned that on the first day. Even if the answer is completely wrong, I give 2 marks out of 10. Even if it is completely wrong, not that answer is correct up to certain extent. No. It's appreciating your presence in the class. By
I
the way,
couldn't submit yesterday, sir. Sorry.
that's the thing.
Kamal.
Is it Abdullah?
Kamal, sir. Kamal.
Kamal. See, Kamal.
Yeah, like I had some issue.
That's right. Make sure that everybody submits. Okay, even if it is wrong, don't worry. You will get it correct. So anyway, I will be telling the correct answer. Okay, probably next week, I will share the mark sheet, what we have got so far. Satish, we can't see you on the screen.
I sent the answer, sir.
No, but until I ask everybody to, everybody that the session is over, in the sense that the question session is over, everybody has to have the screen on.
Okay, sir. Okay, sir.
Sir, I share my answer.
Sorry? Who is that? Is it about how to send the answer, or what? Through the chat, send the answer? Has everybody sent? Oh no, still coming, no? Right. Is everybody done? Right. Can I close it now? Yeah. Seems done. Everybody finished sending. Oops. Shall I close it now? Right. Okay. Looks like it's finished. Right. So remember, first thing is what? Calculate. Oops. Don't send any more. Finish. Oh. Okay. Right. So what we want is to calculate the Z value. Z value is given by plus 1x minus mu divided by sigma. So this is Z1. What is for the second one? Second one is associated with sample mean value. So x bar minus mu x bar divided by sigma x bar. And we know this is equal to x bar minus mu sigma divided by square root of n. That is sigma square divided by n square, which is sigma divided by square root of n. Right. Now, thing is x bar minus mu and sorry, x minus mu x is also 60, x bar is also 60. So that this difference is, numerator is same. Numerator is same. But sigma x bar is smaller than sigma. When the denominator is smaller, this value will be large. So that Z1 is smaller than Z2. So that now we are talking about graph. Since mu is 50, this difference is positive. This difference is greater than 0, is positive. So that we find Z2 to be larger than Z1. So we are talking about left tail probability. So this is the probability associated with Z1. And this is the probability associated with Z2. So that probability Z less than Z2 is larger than probability Z less than Z1. So that probability associated with sample mean is larger than probability associated with the observed value. Okay. Isn't it? That's it. Right. Before we close, any questions or clarifications from today's session? If not, shall we then close the session, since you need to start the other one at 1 o'clock? Okay, so let me now close it.
Thank you, sir.
Thank you, sir.
Okay, you're welcome.
Yes, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you, sir.